students. Welcome to this video capsule on digital design lab. This lab, even though we are going to have it online, the lab have been so designed to make it as realistic as possible and as interesting as possible. So this is going to be the outline of today's presentation. We'll just review the digital gates since this is going to be covered subsequently in the theory classes, but I'll just review what are the various digital gates which we are going to use in the lab. Digital logic families, I'm just going to flash a slide and tell, okay, this is the history of the digital logic families. Towards the end of the theory classes only, we'll be able to tackle this. People, you'll have to understand how these various logic families. So it will be too premature to discuss it out here. I'll just flash a slide on that. And then we are going to use 7.4 series TTL digital ICs for the various experiments, digital lab experiments. So I'll give you a brief introduction to 7.4 series TTL digital ICs. Okay, and all these hardware experiments, which we generally do it on a kit in the lab, now we are going to do it in a software called LTSpice. So I'm going to give you a detailed procedure for installation of the LTSpice and how to import the 7.4 series library into the LTSpice. By default, the LTSpice doesn't have this 7.4 series TTL gates library. So I'll give you a detailed procedure of how to install the 7.4 series library into LTSpice. After that, I'm going to give you the problem definition of lab 1, right? So I will give you one example of implementing one function, and then I expect you to implement the actual problem which will be given to you, right? After that, I'll give you a demonstration of LTSpice installation and simulation. I'll do the simulation. I'll run it for one example, and then you will have to do it yourself. And in the subsequent week, you will have to submit your simulation results to the lab instructor, right? So this is the some of the digital gates which we are going to use. The first gate is S gate. This is, if you give a 0, you will get an output 0. If you give a 1, it will give an output. Then you will say, what is the great fun in having this S? It's not transforming anything. It is because the current carrying capacities may be different. Like if you have an input gate, which is an input gate, wherein it's a function realized by with a complex gate set of gates, but that may not have the current carrying capacity, right? Whereas you can design a buffer like this, which can transmit that input signal without loading the previous stage. So it is like a isolation between an input and the output stage. It will have high current carrying capacity, right? Because if you have to say transmit some data between two chips, right? So you can have a buffer. So this buffer, because between two chips there will be a physical line drawn and there will be a lot of power which will be required. So this is kind of buffer. Okay, it will isolate the input and output. Okay, this is a NOT gate. NOT gate, it's an inverter. It's also known as inverter. 0 will get converted to 1, 1 will get converted to 0. Okay. Then there are some standard AND gates, OR gates, and XOR gates. You can see the truth table. So AND gate is A and B. Both have to be 1, and then you will get a 1. Otherwise, it will all be zeros. And OR gate means either A or 1, right? If any one of them, or even both of them are also 1, then also you will get a 1 out here. An XOR gate is a modification of OR gate where only one of them should be 1, right? And but when both of them are 1, it will be 0. So this gate is also important in many, and in CMOS technology it's very easy to implement an XOR gate also. So that is why this is also an important gate which we need to study. This is a NAND gate. Okay, so NAND gate is nothing but an inversion of AND gate. Okay, so you might be telling, sir, why not only and or why NAND and NOR? Because because to physically realize a gate, okay, whether it be in TTL logic or CMOS logic, you can always implement NAND and NOR functions, and you have to put an inverter to get an AND function. So that is why we always stress on this NAND and NOR. because physically you cannot make transistors. You can't arrange transistors in such a manner the output will be AND. Okay, so once we read about these implementations in our theory class, you will understand that. So just understand that to make an AND gate, you have to make a NAND and an inverter at the transistor level. Okay, but in this lab, we are going to handle only at gate level. So we will have an IC which will be a NAND IC or AND IC. So for you, there is no restriction. You will use an AND gate or a NAND gate or a NOR and a NOR gate. All the gates are available to you for design. Okay. However, in the background, you should realize what happens at the transistor level. So this is an XNOR. XNOR gate is again, if you see, it is just an inversion of an XOR gate. NOR is an inversion of an OR gate. NAND is an inversion of an AND gate. Okay. So these are, now I'm just flashing this slide, just you keep this information in the background. We will be able to touch upon all these logics only towards the end of the course, because you have to know a little bit about transistors and all. So once that is covered in the microelectronics course, only then I will give you details about these logics. Nevertheless, towards the end of the course, then you will know quite a bit about all these logic families also. Okay, so the first logic was diode transistor logic in 1959. It was discrete diodes and discrete transistors used on PCBs to realize digital functions. Then came resistor transistor logic in 1965. Again, this was also discrete resistors and discrete transistors used on the PCBs to realize various logic functions. Okay, after that there came the transistor logic, which are discrete ICs. This is the TTL logic, has been since 1963. Even today it is used. Even in our lab, we are going to use TTL logic circuits. Okay, they are discrete ICs. Okay, now, the TTL logic is not used in microprocessors or VLSI chips. It's a discrete ICs. Okay, you will have an TTL NAND gate, TTL NOR gate, TTL flip flops, TTL counters, TTL adders, but you will not have an TTL microprocessor. Okay, so then came the emitter coupled logic. This was the first microprocessor 3860, which was made using emitter coupled logic. There are 360, 460, 560. So some series of early microprocessors, they all meant a emitter coupled. So these four logics, okay, they were all BJT based, and then came the CMOS in 1974, and till today all the microprocessors are based on CMOS logic, because it is very efficient, area efficient, power efficient, and it can operate at very high speeds. So that is why CMOS, since 1974 we are using CMOS technology. It's not that the same CMOS technology we are using it. In 1974 an Intel 4004 chip was launched, which had only 2000 transistors in it, and the device had a 10 micrometer channel length. As of now, we are working on in 2020 7 nanometer transistors. Intel has not come out with 7 nanometer, but other companies have come out with 7 nanometer chips, and the channel, and there are billions of transistors in a chip. Okay, this is just to give you a rough idea on what are the digital, but we are essentially going to work on transistor logic ICs. Okay, this is an first IC which I am going to discuss with you. This is known as a NAND gate IC, which is 7400. Okay, it is quad 2-input NAND gate. Quad means there are 4 gates. 2 inputs means it has got 2 inputs each of these gates. So if you see the pin configuration, there is a notch out here on the pin. Okay, and then this is how the number. This is a standard for all the ICs. There will be a notch when you look from the top of the IC. The pins will be on the bottom. Okay, so you will number it 1 2 3 4. So this is the skill, and every IC will require an VCC and ground. Okay, for TTL logic, the VCC is plus 5 volt, corresponding to logic 1, and ground is 0 volt. This is specific to TTL gates. Okay, so in our experiment, for all logic 1, we are going to give 5 volt, and for logic 0 we are going to give 0 volt. Okay, this is not the same for every logic. Okay, 5 volt is not a universal logic 1. It could be 1 volt, it could be 1 volt, 2 volt, 3.2 volt, depending on the various logic families. So in our case, we are going to use TTL gates, and hence VCC is 5 volt and ground is 0 volt, and accordingly logic 1 is 5 volt and ground is 0 volt. Okay, so this is going to be the quad chip NAND gate. Okay, this is how the chip would look like. You will find there is a notch here, there are pins available here. So various companies have, TI has got, Fairchild has got, everybody manufactures this 74 series of gates. Essentially the pin configuration would remain the same, and any, the brand could be anything, but the more or less the functions, pins will definitely be the same, and but they might differ in terms of their speed of operation and power consumption little bit. Otherwise 5 volt TTL, it is fixed. The pin configuration for these ICs will be fixed. Okay, inside each NAND gate is like this. Okay, again, we are not going to learn this now. We'll learn only towards the end of the course. Just to give you an idea, okay, this is how each NAND gate will be made. There will be few transistors, diodes, resistors, and all. And this is the circuit of a NAND gate. You will understand the basics of this. And if you see, these are the inputs, these are the outputs, and you require VCC and ground also for the circuit to function. VCC and ground also for the circuit to function. Okay, to know more about these, but any IC, you can always download the data sheet from the net. Okay, if you type data sheet of 7400, you will get. So every company provides, like a Fairchild provides its own data sheet, and TI will provide its own data sheet. So that will give the specifics of that particular chip. So the chip, it will give the pin configuration also. You see the pin configuration is given here, and it will give the truth table also. It will also give you the power supply voltage. Okay, and now from the data sheet you can see that the nominal is 5 volt, minimum is 4.75, and maximum is 5.25. So this is the VDD. Okay, and it will also give you some other information like high level input voltage, minimum is 2 volt. That means any voltage between 2 and 5 volt, 2 to 5.2 volt, in fact it will be considered as logic 1. Okay, and it will also give you information that low level input voltage is 0.8 volt. That means any voltage between 0 to zero point 0.8 will be considered as logic 0. And what about 0.8 to 2 volt in between? Then it is Bhagwan Bharose, right? The output, you may not get any output, desired output. It will throw some muck outside, right? It will give you some spurious signals outside. So your digital signals, you know, so the limits will be specified by each manufacturer. Okay, although 5 volts is the norm, 1 volt, but you can give anything between 2 to 5 volt also, the IC will consider it as 1. Similarly 0 is an ideal 0, but anything between 0 to 0.8 volt will be considered as 0. So why this margins and all, you will understand once you understand how the circuit functions. Okay, right now that information is not required. I'm just giving you a rough idea, right? When you make this when you make an IC, when you breadboard connections, you will see that okay, this is pin 1 and 2, they have given some inputs through these blue switches, and on from pin 3 they have taken an LED, and on pin 7 the ground is given, and pin 14 the VCC is given. I'm just giving you a brief ideas that when you make an actual circuit on a PCB or a breadboard, you need to not only give input and output, you also need to give VCC and ground also for this IC to function. We have seen in the circuit diagram it requires an VCC and ground, right? But in the LTSpice model, what we are going to do, we will pick up components like 740. If you pick up a NAND gate, it will have input and output. We don't have to bother about the VCC and ground. Once we pick up this model, the software will automatically give the required power supply to that IC. So we don't have to make a connection of VCC and ground. But now, after 6 months, and you will be so used to LTSpice, so don't think that you don't require VCC and ground. When you are actually doing something practically on a circuit, remember that you will require an VCC and ground. And 7400 is an quad NAND gate, but in the model when we pick up, it will just pick up each gate separately. Okay, because otherwise every time you click on an 7400, if it is going to give me 4 NAND gates and I just require 1 NAND gate, the circuit will look clumsy. Okay, So, but in the practical circuit, even if you want to use only a single NAND gate, if you are going to design a PCB, you might have to use an 74 IC and leave the three NAND gates blank without any connection, right? So that is the difference. Okay. Now there are some other ICs like 7402 will be a NOR gate, 7408 will be an AND gate. So you don't have to remember all these numbers of these gates. And we'll see, and you will be able to pick up from the menu. You will be able to see the symbols. So seeing the symbols, you will be able to pick up what IC you require. So you don't have to really memorize these numbers. Similarly, there is an OR gate, there is an XOR gate. Okay, now I'll give you a brief introduction. I'll give you a brief procedure for installation of LTSpice. Okay, what you're going to do is you are going to go to this link, right? It is sanjayvidyadharan.in stroke downloads D is capital. So you will find one zip folder named LTSpice underscore installation underscore files.zip. So download this zip file. Okay, unzip. Okay, once you unzip, there will be four files inside that. Okay, the first one is the LTSpice installation.exe file. The next will be 74ht library. Okay, this is a spice model. .lib means it is a spice model. Okay, so this model we need to incorporate it into our LTSpice. I'll show you the procedure also. Okay, then there is a sim folder. Inside the sim folder you will have 20 files which are symbols for various ICs. Okay, and then I am also going to give you one example file which I am going to actually demonstrate you now how I'm going to give an example demonstration, and I'm going to share that example file with you so that you don't have any problems. Okay, so after having downloaded these files, you are going to run the LTSpice. That will install the LTSpice on your PC or laptop. Okay, now once you have installed, so it will generate a shortcut. You click on that shortcut. This is the window which will come up. So you go to file, new schematic. Okay, you press it on the new schematic. Once you press on the new schematic, right, a window would open like this. In that, here you have a small tab which is known as component tab. It looks like an AND gate. Okay, you because if you press on that AND button or the component button, a window would pop up, and here you will find one address, right? Okay, a path. We'll note down this path. Okay, the path in my case it is C program files and LTSpice and something like that. It could be different on your laptop. Okay, so this path is important. Why is this path is important? This is going to indicate us where are the library for files stored. So we got to put that 74 series files on also. So we will just note down this path. Okay, once you have note down this path, so this is like in my case it is C program files LTC, then LTSpice, then lib. Okay, inside this lib file there will be two folders. So you have to from this window you will find out what is the path, and once you have found out what is the path, okay, you will go to that library. So there is a lib path. Okay, lib. So this is the path which you will see there in the window. Okay, like lib dot symbol. But I'll go one step and one step and ahead. In the lib file, okay, in the lib file there are two folders. One will be sub, one will be symbol. In the sub file, I'll have to paste this 74CT. No, it is 74HCT. Okay, sorry, just note down that it is 74HCT. Let me do that. It is 74 hct.lib file. Okay, this lib file you're going to paste it here. Okay, which we have downloaded. From the address which I have given you. So this lib file you're going to put it in subfolder, and then you are going to open the sim folder. Right, in that there will be 20 files which you have downloaded. Okay, the 20 symbol files. Okay, you're going to copy all 20 of them and paste it in this lib stroke sim. Okay, is it clear? In the lib folder, there will be two folders. One is sub and one is sim. In the sub folder, you are going to paste 774 and a hct.lib file, and in the sim folder, excuse me, in the sim folder, you are going to file. Don't put this sim folder into this sim folder. Okay, the contents of this sim folder, there are going to be 20 symbols. Those individual symbols you are going to put it in this. Okay, there will be a lot of symbols already available in this symbol, so just put these also into that. Similarly, in the subfolder there will be so many other files also available. You just have to put this also into that subfolder. Okay, once you have done that, then you will then you will have to shut down your LTSpice and reopen it once. Okay, once you have done that, okay, you have to now give the spice directive. Okay, so here in the corner of those, when you open a new schematic, again you will go to file, new schematic. On the side there will be something known as spice directive. You will click on this, you will get a window like this out here. Okay, so it has got comment and it has got spice directive too. So comment is there, spice is there. So you are going to use not the comment one, but you are going to use the spice directive, and you are going to type dot include 74 hct dot lib. Okay, so this is the lib file which we have pasted there. Okay, so now you are going to tell LTSpice, okay, you use that libs file also for your simulations. So once we do, you are to type that and press OK. So once you press OK, you then you will be able to paste that comment out here on this. Okay, once you have done that, again once we go to the component tab, you will find that all those 74 series which I said, they are all available in the, they are all available in the component. So you can when you click on each of those things, those symbols will come up here, so that you can pick up the required and get. Okay, once you have done this, you will be able to click on the component button and you will see all then you will be able to drag, click OK, you paste it here. Okay, I'll show you the demo also, so that will clear further all your doubts. Okay, so once I've done with this presentation, I'll open up an LTSpice and I'll clear rest of your doubts there. Okay, so now coming to the problem definition for the lab. So this is the sample run. I am going to give you a demo of this circuit. Okay, the function which I am going to implement is AB plus C. Okay, so I am going to implement it with one NAND and one OR. Okay, A and B and OR. Okay, I'll show you this how is to be done in the LTSpice, right? So once you have made these gates, you have to give some test signals, right? So I'll tell you how to give pulse signals. Okay, A B C, so that A B will C will change accordingly and you will be able to see. Now if you see A B C, you don't have to really pull a wire from the source and keep connecting to A, from B to B, C to C, right? You can name it this wire as A, and you can name this wire also A. So automatically the software, when it runs, it will assume they are connected. So this is, otherwise your circuit will become very clumsy, right? If you're making say 10 gates and A is to be given at 10 different places, you will keep pulling all the wires to all those 10 places. So the better option is to give A, B, C names and connect it. So if you have 10 gates, you just have to keep giving appropriate names, so they will get connected. So this B will automatically get connected to B. So okay, so I'll show you this, I'll demonstrate this, and then I have to like three, there are three signals, right? I have to give. So there could be 8 combinations, right? 8 different combinations. For A, I am going to give 1 microsecond time period. For B, 2 microsecond, and for C, 8 microsecond time period. So within 8 microsecond, I'll get the desired outputs. All for all the three combinations at 8 microsecond, I'll be able to get the desired output at F. Once I run the simulation, I'll be able to plot these waveforms. If you see A, B, and C, when C is 1, it is like the output will be 1, and when C is 0, only when A and B are 1, this will be 1. So the last one at the bottom is the output. These are the three inputs. So I'll demonstrate you how this is going to be done, right? Okay. And then we also are going to implement the same AB with NAND gates. Okay, right? So why again I told you, like, because the NAND gates are universal gates. Okay, so that's why it's important that we learn how to implement things with NAND gates also, because AND gate will be made only. It's a combination of AND gate and inverter inside the gate at when I'm speaking at the transistor level. Okay, so this is an AND gate. So you need to need is equivalent to actually an OR gate. If you invert the inputs and the output, an OR gate will become an AND gate. Similarly, if you invert the inputs and the output, and AND gate will behave like an OR gate. So you can verify this from the truth table, right, of an AND gate. Just try to invert the and the in the truth table, and you will find that if you invert the inputs and the outputs of an OR gate, it will be an AND gate. So okay. So now in an AND gate, in an OR gate, if I just invert the inputs, okay, I don't invert the output, then that will be a NAND gate. Okay, because see, this is like if I put only in dots out here, and to compensate for this dot, I put one more dot out here. Okay, the dot means inversion. I put one more inversion. So these three inversions will become a NAND gate. So that will remain outside. So that will become a NAND. So if you have an OR gate, if you are just inverting the inputs and not inverting the output, that will become NAND. But if you are inverting the input and output, then it will become AND. Okay. So this is how. So for our function, initially we had one AND gate and OR gate. Now I have to implement it with only NAND gate. So I'm going to put two inverters like this here, right? They'll cancel each other. Similarly, I'm going to put two inverters out here. So they are also going to cancel each other. So once they cancel each other, if you see this NAND and this inverter, I replace it with a NAND. Similarly, this is an OR gate where only the inputs are inverted. So that will become a NAND gate. Okay. Now there is one inverter. So I am going to use an NAND gate with input shorted. So this will behave like an inverter. Okay. You see. So now the same function f is equal to a plus b plus c has been implemented with three NAND gates. Is it okay? So this is how, this also I am going to demonstrate to you. Okay. Now what this I am not going to demonstrate, do the demonstration, but you are expected to do this experiment yourself and then show the results to your lab instructor in the next class. Okay. So what you got to implement is a majority circuit. Okay. What is a majority circuit? You have three inputs ABC, and F is the majority output. Okay, so even if only when there are two or more ones in the input, it will give an output. So there are four different combinations, right? Like if B and C are one, you should get a one. Similarly, if A and C are one, you will get one. A and B are one, you will get one. And if all the three on, for all other conditions, then there are no two ones, so it will be zeros out here. Okay, zeros out here, zeros out here. So F can be written like it is A and B, or B and C, or C and A when they are one, or ABC. Now if you see ABC, this is a redundant expression. Okay, so we need not use this. Okay, time being, you might ask me, sir, how do we come to know whether this is a redundant gate or not? Okay, that will learn in the theory. Okay, right now I'm just telling you. Okay, this is going to be redundant because ABC one means AB is one. Okay, so you can just neglect that. So this is the function which we need to implement. Okay. Now, if you see with AND and OR gates, you are going to implement it like this, and you are going to give the test signals. Like I am going to give you a demo for the first function, that is AB plus C. You are going to implement it for this circuit. You are going to give the test signals. You are going to generate the waveform for all combinations of ABC and show it to your instructor in the next class. So you will have one full week with you. Try it out in your own house. Okay. So the instructor would ask you specific questions about how it is implemented, and he might ask you to change the circuit and show some simulation. So don't try to copy. Okay, try to do it yourself. It is pretty interesting. It is pretty simple. So if you do it yourself and even your final exam is going to be viva, where we will be you will be asked to make the circuits and online will be you will be monitored, okay, through an on although it is going to be online, so it is going to be difficult for you. There is no batch wise concept here, it is all individual wise, so I suggest you do it yourself, right? And if you have any doubts whatsoever, 24 into 7 whatever time, you can pick up a phone call, you can send a mail, you can get in touch with me or your instructors, and you can get my phone number and email id on the BITS faculty webpage, or you can get into touch with your lab instructors. Okay, take this course seriously, it's pretty interesting and easy. Okay, don't try to copy the circuits from your friends and waste your time and our time. Okay, so you're going to implement this using two input AND gates. And okay, the 7-4 series doesn't have an three input OR. Okay, so you got to use uh, two input OR gates like this, which is shown here, to implement a three input OR gate, right? So similarly, you are going to make it using only NAND gates also. Okay, you're going to implement, but you have a three input NAND gate also available in the TTL series, so you can use that. Okay. Now, when you submit, once you have done the simulations and you have shown your circuit to your instructor during the lab hours, okay, this you will do this exercise offline, right? I'll be publishing it 1 week in advance, and you will do the lab experiments in your own time at home. And during the lab hours through Google Meet, you are going to submit this assignment to your lab instructor. Okay, once you're going to do that. Okay, so just before submission, and we saw how to write this spice command, right? There was also an option of there in that window. You also had an option of command, right? So comment. Okay, so in the comment, if you write your name and you got to paste it here in the spice folds, and then save this file with your roll number and share it with your instructor. Okay, so you need, once you complete your experiment and your viva, what you got to do is you got to save your schematic. In the schematic, you are going to write your name, okay, through the comment spice directive. You will click on the spice directive, you will click on the comment, and you will write your name, and you will save the file. You will name the file with your roll number, and then you will share it with your instructor. They will let you know which is the folder wherein you got to upload these files, which will be kept as a record. Okay, now I'll demonstrate you how to install LTSpice, and I'll give you tips about how to do the carry out the various simulations using LTSpice. Now I'll give you a demo of how to download the LTSpice installation files and install it and run simulation. So you're going to go to Sanjay Vidyadharan.in downloads. This is the link which I provided to you. So you will find one LTSpice.zip file. Just right click on it, and you'll be able to just click on it, and you'll be able to save this file onto your desktop wherever you require it. Okay, so I'm going to download it. Okay, this is the LTSpice. It's a zip folder. I'm going to unzip it, and once you unzip it, you'll find there are 4 files in it. The first one is ltspice.exe. Okay, so this, if I it will ask you whether whether you give the permission for it to get installed. So you keep clicking yes, it will install it on your desktop. Okay, so once you have installed it, you will get an shortcut on your desktop. So I click that. So this is an LTSpice schematic which has opened up. So I go to file. Okay, new schematic. Okay, so it's a new schematic. Okay, you have to press the file new schematic, only then all these icons will be. So this is a new schematic. Okay, I go to the component. There is a component tab. Okay, I'm going to press that. So you will see lot of components are already there in the LTSpice. These are the components which come along with the software. Okay, you have an LED, you have you have a Zener. Okay, there is a digital library also. If you click on the digital library, it gives you some standard few components are there. We are not going to use them because they are universal ones and not specific TTL. You will have to do the program and they're not complete also. Okay. So what we are going to do is we are going to install the required components here, right? So now where to install that? Okay. So the path will be shown here. Like in my case, it is C program files LTC, LTSpice, then lib, then sim. Okay, so I know. Okay, this is my lib folder. Okay, so the path for this is seen from here. Okay, once I see that path, okay, let me close these windows, close the LTSpice also. Okay, now I'm going to open the folder here. This 74HET lib file. I'm going to copy this file and I'm going to my computer, C program files. Okay, this path is specific to my laptop. In your whatever wherever you have installed, you will have to check that path. Okay, so I have gone to this PC, then C drive program files, and then it says LTC. Then inside LTC there is an LTSpice. Inside LTSpice there is one lib file. Okay, don't paste it here. Okay, lib file. Inside lib there are three folders. So I am interested in sub. I go to the sub file and I am going to paste this. Okay, continue. So I have inside the lib file I have pasted this file 74het.lib. Okay, again I come back to the lib folder. Inside the lib folder there is a symbol folder. If I open the symbol folder, there are not many files which are already there available here. Okay, so I minimize that. I am going to the folder which I have downloaded and here in the zip. Now here you say I have given symbols for around 20 ICs which are required for us. Okay, this is not the complete list, but these 20 we are going to. So I am taking Control A, Control C. I am going to copy all these files, and what I am going to do is where is the symbol? Okay, this is the symbol folder in program files LTSpice and LTSpice lib, and inside that there is symbol. I am going to paste all these files out here. Okay, right. Okay, so I have now successfully imported all the required library into LTSpice. Okay, now I am going to reopen LTSpice. Okay, then I am going to file new schematic. Okay, now I also have to give a instruction to the LTSpice that you need to use this. So I click on this. Okay, this is spice directive. So I am going to type dot and then include 7hct dot lib. Okay, I press OK and I'm going to put this spice directive in the schematic. So this has to be there in every schematic. Okay, so every time you open a schematic, new schematic, you got to type this spice directive. Now I go to component. Now if I go to the component, you will see earlier these were not there, right? Now you will find, see this NAND 740 NAND has got, this as NOR has come. So you don't have to remember the numbers because as you keep clicking on these ICs, the schematic figure will appear. So I have to implement F is equal to AB plus C. This is what I am going to demonstrate to you. So let me pick up an simple OR gate, right? Okay, and I also have to pick up. I'm going to again. I'm going to press the component button, and this is NAND NOR. I require an AND gate. Okay, 7408. Okay, I have put an AND gate. I require. Okay, that's all. Right. So I got to interconnect this. Okay, so how to do the interconnection? This is the wire. Okay, the blue with the line. I'm going to click on that wire. I click here once, click here once, click here once, and then double click it here, and click here once and press escape button. So this has got connected here. Now I'm going to click here. I'm going to click here. I'm going to click here. So I have connected a wire there. I am going to click here. I'm going to click here. Okay, I have connected a wire there. I have clicked here. I have clicked here. I'm going to click here. I'm going to click here. Right now, this is A, B, or C. Right. Okay, so this is schematic is done. Now I'm going to component and I am going to go to the voltage. Okay, so voltage source. So I'm going to pick a voltage source here. Right. So I can use the mouse to scroll and zoom and things like that. Okay. So now this is the now I'm going to put a wire out here. Put a wire out here. Put a wire. Okay. I'm going to put a wire out here, and I want to put a wire out here, and I am going to let me. This is the ground. Okay. So I'm going to give a ground here, right? One. Now I have to set. So this is a DC source, but I require a pulse source. So I go to advanced. Okay, I go to pulse. Okay, so initial voltage I am going to give 5. Okay, always remember, give initial voltage 5 and the V on as 0. Okay, you might think you want to give an initial voltage 0 and give it 5, but no, it is better to give it 5 and 0 here, because you will get a correct waveform. Otherwise, you will get an inverted waveform. Okay, so this. So I don't want to give any delay. I am going to give 1 picosecond. You got to remember these things when you do it. Okay, you got to give a fall time 1 picoseconds. Okay, T on. So I am going to give 1 micro. Okay, period I am going to give 2 micro. Okay, so I am going to give. Okay, so this is the source. So let me just organize this a bit. So see this is drag. Okay, you click on drag. Okay, and if you click on drag and then try to move. Okay, it will come along with the connections. Okay, you know, this is the move button. If you press the move button, it will not bring along the connections also. It will just move the particular component. So let me put it back. Okay, now let me just move this entire thing over here, right? So I am going to see, I can always connect this input A like this here, here like this. I can do that. Okay, but I prefer not to do that, because it's going to make the circuit uh, look clumsy. What I am going to do is, I am going to put a wire here. I am going to right click on here and label net. Okay, I am going to give a label to this, which is A and A. So this has got connected. Okay, even though you are not drawn a physical wire between these things. Okay, let me move this and keep it here. Okay, now I got to give B and C also. So I have an edit duplicate. Okay, so I put this here, right? And I'm going to change the frequency out here. So I'm going to right click here and I'm going to change the frequency to 2 micro and 4 micro. Okay, and then I am going to rename this as B. Okay, and I'm going to add label net B here. Okay, so the B is also now connected. Now I got to connect C also. So let me do edit. I can pick up another voltage also. You can do that also, but since we have this copy paste option, let's use that. I'm going to put this. I'm going to right click here. I'm going to give now 4 micro, and I'm going to for the part B which you are going to do yourself also, please use the same sources, so that within 8 microseconds we get all the combinations. I am going to in fact save this file and I'm going to share this also with you people. Okay, so I right click here and Okay, this we have already done. We need to change the net name. I'm going to give it as C. Okay. Here I'm going to label the net as C. Okay. I'm going to put it here, and the output node I'm going to put it as F. Okay. I'm going to get. Okay. Now let me run simulation. Okay, if I run the simulation, it would come. Okay, what type of simulation you require, right? So I require a transient simulation. Okay, and I require it 8 micro. Okay, could not open include 7 HCT drive. Okay, yeah. I think that error is because I goofed up with the Spice library. So we have to give Spice library directive here. Okay. I think I selected the wrong option. I'm writing include 74HCT dot lib. Okay. This second one, spice dot lib directive. Okay. Okay. So it is include dot. Okay. Again, it is dot lib. Okay. So now let me run it. So I'll get a waveform window. So this is a blank waveform window. So I need to, so if you see this, when you move your cursor on the schematic, you'll get one this red, what holy pichari kind of thing. Okay. Probe. Okay. So I am going to put it on A, and I'm going to put that red one on B, and I'm going to put it on C, and I'm going to put it on F. Okay, the other one also, when you move around, you'll get one more. Okay, this is an heart shape with a round thing and an arrow going in. Okay, this is going to plot the current, which is okay. We are not presently interested in the current. So I have all the four plots out here. So I'm going to maximize it. Okay, so there are four. So you can't really make out now what is the transitions happening. So I do a right click, right, and add plot pane. Okay, and add plot pane. Okay, now I'm going to simply drag this A here, B here, C here. You see? Okay. So it is what is this function? It was A and B or C. So or C means whenever C is one, if this is one, so this is one, and whenever C is zero, A and B. So this is the conditions A and B. So I have used these particular frequencies and a sweep time of 8 microsecond. So you will see all the 8 combinations of ABC is available below. So for your next experiment also, please use the same kind of input signals so that you can verify for all your input combinations. Okay. So this is the part one of the experiment. Okay. Demo which I have. Now we're going to implement the same function using NAND gates, right? So I am going to cut this, I'm going to cut this, and I'm going to take a NAND gate, okay, 7400, okay. I'm going to put one NAND gate here, I'm going to put the one NAND gate here, I'm going to cut this C here, I'm going to move this entire thing slightly above, because now I have to have one more NAND gate here for C also. So I'm going to have 740 and get one more out here. Right. I'm going to drag now this a little bit forward. Okay, I'm going to connect this wire from here to here to here. Okay, going to cut this extra length of wire. I'm going to again take a wire here, 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 here. I'm going to connect this, and I'm going to label this night as C. Okay, I'm going to label this net as C, right? So now I'm going to run the simulation again. Now this is the same function A, B or C implemented with only NAND gates. I'm going to run the simulation and you see I'm getting the same waveform. Is it okay? So now for you, no, you can try this out as a practice and then you can implement the majority carrier. Okay. Once you have implemented that, you go to the spice directive. Okay. Or you can go even to the text button, right? And then you can do the comment. Okay. In the comment, you can write your name. Right? Okay, I'm going to place this. I'm going to file, save as. I'm going to save it as example one. Okay, on the desktop. Save. Okay, then I can close this window. Okay. Now, if you see, that file is available here, example one. You are going to rename this with your roll number and you are going to share this file with your instructor. Okay, that's all for this lab. Okay, the next lab, I'll show you one more experiment on LTSpice, and at the end of that lab, I'm also going to give you some kind of extra assignment which is not compulsory at all. Only those students who are interested in learning a little bit, or that has nothing to do with evaluation. It has nothing to do with your course syllabus, your final exams. It is just as an hobby project. So I'll give you one or two small specific problems at the end of the lab video, which I'm going to put it online. Okay. So all the best and do well. Again, let me tell you once again, don't try to copy. These can be shared between one student to other, but you will be the loser. Okay, no instructor will lose anything, but you will be the loser. So it is better you try to do it. In case of any problem whatsoever, feel free to call up us. Preferably, you should have a TeamViewer installed, and you can send me the TeamViewer ID so that I can log in remotely and see what is the problem and resolve that. Okay, and even the first week of the lab, because this video will be available to you on 17th. So in the week from 17th onwards, in that week, you can do this experiment at your home in your own time. But during the scheduled lab hours, if you have any problem with the installation, you can get in touch with your instructor. So that particular week will be dedicated only clearing your installation related doubts. But from the week starting 24th, okay, on 24th, I will release the video for the second experiment. And but that 24th week, you will be able, in the lab hours, what you will do is you will share your files and simulation results with your instructors. So, okay, that's all for today. See you next week with the next video. Thanks a lot.